I think this could be a good time for us to start.
Okay.
Yeah, sorry to interrupt. So right, cool.
Uh,
Right. Yeah. So, well, thanks a lot, Jacob, for coming. For all who don't know him, he got his PhD from Stanford University, and he is now a faculty in the Department of Statistics at Berkeley, UC Berkeley, and he's also involved in the Open Philanthropy Project and OpenAI. And today, Jacob is going to talk to us about the science of measurement in machine learning. So off to you, and thanks again for coming.
cool. Thanks, Giovanni, and thanks everyone for inviting me. I guess the one positive thing about COVID is that it's easier to give these talks at lots of different great places. I've never actually been to the Turing Institute, but I hope to come sometime when it's safer to travel. Um, So as Giovanni mentioned, I'm going to be talking about the science of measurement in machine learning. And since it's maybe not a topic that will be familiar to everyone, I want to start by kind of saying what I mean by this. So I guess first, let me just define measurement. So for me, measurement is a way of extracting data from, I guess, from anything, but for this talk, from a machine learning model that bears upon some important hypothesis. And uh, and you might think that we do kind of lots of this in machine learning, but I want to argue that we actually don't. And in that sense, we're kind of a pre-scientific field, and this is going to be one of the main ways we become an actual scientific field. So why am I making this claim? Well, machine learning is extremely empirical, but we actually obsessively focus on just one measurement for the most part, which is just the test accuracy. Maybe sometimes we look at test accuracy on multiple distributions, but often actually there's even just like one distribution we care about. But there's many other ways that we could measure a machine learning model. We could try to understand, for instance, the variability across random seeds. We'll see later in this talk that actually a lot of phenomena that you might observe are actually just reading into noise in the sense that they kind of go away if you vary the random initialization seed. There's other things you could do, like try to visualize your model, look at, say, what images like lead different neurons to be more or less strongly activated. You could look at how the training data influences model prediction. So there's lots of ways that we can try to measure models. And I think we already know this intuitively. If you have an ML model and it's not working and you're trying to debug it, you don't just look at the test accuracy and change things until it goes up. You kind of like print out all sorts of intermediate diagnostics and sanity checks to see what's going on. So I think, the case where it really matters to us when trying to get things to work, we do this, but we maybe don't do it enough in our research papers. So aside from that kind of conceptual argument, I think there's actually a lot of historical basis for why measurement is extremely important for driving forward science. So I think if you just kind of read the history of science, I guess this is kind of my side hobby when I'm not doing ML research, is I read history, and I'm particularly interested in the history of science. It really has just been the driver of lots of important discoveries. So one example was the microscope, kind of led pretty directly to the discovery of lots of interesting things, spermatozoa, red blood cells. Red blood cells then also played a role in crystallography also played a role in red blood cells. So crystallography was this imaging technique that helped understand the structure of DNA, the structure of proteins. Red blood cells, I think, were one of the things that were imaged with that. And I guess one thing that's kind of interesting is that in the mid 20th century, there's a kind of Moore's-like law for crystallography that's kind of similar to the Moore's law we see for computers. I guess this was before Moore's law was articulated, so it didn't have that name, but if you kind of look at interviews with scientists, you can kind of see it going on. So here's an interesting quote that I found from Francis Crick, who was one of the discoverers of DNA. So he said, as you know, at the atomic level, X-ray crystallography has turned out to be extremely powerful in determining the three-dimensional structure of macromolecules. The list of techniques is not something static. They're getting faster all the time. We have a saying in the lab that the difficulty of a project goes from the Nobel Prize level to the master's thesis level in 10 years. And so I think this hopefully kind of underscores the kind of rapid development of this measurement technique of crystallography and how it really drove forward progress. And at least I would argue, and I don't think this is, I don't know if everyone would agree with me, but I don't think this is a controversial claim either, is that sort of rapid mid-century progress in molecular biology was kind of driven, it wasn't just driven by crystallography, but it was driven by kind of symbiosis between new discoveries that kind of drove the need for better measurement that led to more new discoveries. And it wasn't just crystallography, there were lots of other measurement techniques as well that kind of played a role here. So kind of given this, I think I could have given other examples as well, but maybe since this is a talk about ML and not about the history of biology, I'll kind of leave that there. But I think kind of given both this sort of conceptual argument and this historical track record, it's worth reflecting on in machine learning what actually does drive better or cheaper measurement. And so I think there's three big trends that help us measure things in machine learning. One, maybe the one that we're most familiar with, is just cheaper computation, because all of the measurements we perform are basically running some experiment on a computer. If it's cheaper to do that, we can measure more things. And so that's that's one kind of fairly straightforward one that's similar to this kind of Moore's law for crystallography. Another is kind of new paradigms that allow us to kind of probe systems in ways that we haven't before. So one example is style transfer, or more generally conditional generalization. So actually, I think Philip Isola has made this point kind of interestingly. He calls it data plus plus, but the idea is, right, before we were kind of limited to data that we could collect. So you could, train a model on data, you test it on data. Data is kind of how you kind of understand what models are doing. But when you can do things like conditional generation or style transfer, where I can kind of generate images that don't really exist with interesting styles and kind of combine different styles and things like that, then all of a sudden I can create much more diverse data than I could before. And I think, for instance, in understanding the outer distribution robustness of models and kind of how they generalize, this has been a very useful tool, combined, for instance, with automated rendering software, which is maybe instead of using machine learning to do conditional generalization, it's just using human-made software. But both of these are kind of this way of getting more rich data that you can kind of collect in the wild. And then another example of a paradigm that I think lets us kind of study models in more ways than we have before is few-shot learning, because we no longer need huge data sets to kind of understand a model's capabilities. Even just a small number of examples can kind of let us try to understand what a model knows, and that's been combined with other more recent techniques like prefix tuning. So I think this is kind of the second big thing. And then the third one, which is actually what I'm going to focus on in this talk, is better statistics, because all of these measurements are noisy. I kind of alluded to this with this claim about random initialization noise. It actually turns out that the average test accuracy, the thing we're used to measuring, is kind of uniquely non-noisy and stable. And once you move away from that, actually there's a lot more noise to contend with. And so if you want to understand what reliable signals you can extract from all of this new and more rich data, you actually need a better statistical methodology to handle that. And so that's what we'll be talking about today. So that's kind of my philosophical spiel. I'll jump into kind of more technical details next. But are there any questions so far? Cool. And then I guess we were kind of, before the talk started, we were kind of talking about aligning AI systems with humans and kind of making AI more trustworthy. So I think there really is a direct link between measurement and trustworthiness. You can trust systems more if you can understand and predict them. You can do that better if you know more about them. So I think measurements provide information, which leads to better understanding. That's maybe one route. But you can also think of measurements as a form of audit, where you kind of expect a system to behave a certain way, and you can kind of check if it actually does. And I think there's lots of things that look kind of like audits. So there's these things like counterfactual annotations, where you kind of change something that should change the label and check if it actually changes it the way you expect. I think adversarial robustness is a good example of a kind of audit-like measurement, where you're kind of searching for problems. I think feature visualization, also kind of is in this category where you're trying to understand if neurons are really responding to semantically meaningful things. So I think that's kind of just an aside, that I think there is this important link between these two things. Okay, so in this talk, I'm basically going to spend the rest of the talk going over two different case studies from our group in kind of measuring a new type of thing and the statistical challenges that arose in that. So the first is going to be trying to understand not just the average test accuracy, but the test accuracy at the level of individual data points. And then the second is going to be looking at measuring the similarity between different latent representations of different neural network models. So let's start with this kind of data point level question. So to frame this a bit more, average test accuracy, which again is I think what we typically pay attention to, is not really the whole story. So I think there's more and more papers coming out that I think are making this clear. Aside from just the question of out-of-distribution robustness, it turns out that sometimes you can do worse on rare subgroups even as you're doing better overall on average. And also models that, I guess models that behave fairly similarly in distribution can actually behave fairly differently out of distribution. So you might have thought, well, we have to worry about out of distribution insofar as things can get worse out of distribution, but maybe in distribution is a good predictor. But that turns out to not necessarily be true. It's true in some settings, but not in all settings. And so I guess we want to kind of zoom in to kind of understand things on a more fine-grained level than just the overall test accuracy. And I would argue that at least for the data you have in front of you, the most fine-grained you can possibly go is to just look at individual data points. And for instance, we could ask questions like, as we change the model architecture, or as we make the model larger, or maybe as we train on more data, how do the predictions of individual data points change? And so that's what we're going to do. But it turns out that this is quite noisy, so we're going to have to be careful. And so I guess to say what I mean by noisy, I need to kind of define what I consider to be signal and what I consider to be noise. So I guess examples of signal are things I kind of talked about already. If predictions are changing because I've changed the model architecture, or changed the model size, or increased the amount of data I have, or trained on a richer training distribution than I had before. Those are all things I would count as signal. Those are things I kind of care about. But things that I would consider to be noise are things like the random initialization seed of the model, the like cross validation split between train and test, which I guess you could also think of as a random seed. But you know, these are things that that I am going to consider noise. And so we want kind of measurements that are sensitive to the signal, but not to the noise. So for instance, if data point level predictions are just changing all the time just for the random seed, then we're going to kind of be in trouble. So we should understand how often that happens. And so this table is kind of my best attempt to summarize what happens, where the short answer is that actually there's a ton of noise, and you actually have to be quite careful about it. And I think this is something that's underappreciated. So I think maybe even just if the only thing you understand from this talk is kind of this empirical picture I'm about to paint, I think that would already be I'd be quite pleased. Okay, so what are these numbers? So this is a natural language processing task where we trained different variants of the BERT architecture, so different sizes of the BERT family of models, on a language task which is predicting semantic entailment. I think the details of the test don't matter that much, but basically it's a three-way classification task where you're given a pair of sentences. You have to either say A entails B, B entails A, or neither entails the other. And so these models are first pre-trained on just a large amount of text from the internet, and then they're fine-tuned on this classification task. And so there's two different random seeds. There's the random initialization of pre-training, and then there's also the random seed for fine-tuning, which will affect things like the data order. And so these are kind of the two random seeds. And so there's 4 columns here. So the first column is just the accuracy of these models. You can see sort of unsurprisingly that as I make the model bigger, it becomes more accurate on the test set on average. These second 2 columns are looking at on how many data points does the model make a different prediction if I change the random seed. And so this first one is if I only change the fine-tuning seed. And the second one is if I change both the pre-training and the fine-tuning seed. So this is showing that about 7 to 8% of data points have a different prediction if I just change the fine-tuning seed, and 10 to 11% have a different prediction if I change both of these random seeds. Now note that the difference in average accuracy is only 9.5 percentage points. So actually the number of individual data points whose prediction changes is larger than the difference in accuracy. So presumably what's happening is like a bunch of data points are changing, but some of them are changing to be correct, and some of them are changing to be incorrect, and it kind of averages out. And you can actually see that by looking at, this is the standard deviation in accuracy across random seeds. So this is the average accuracy. So even though 10% of my predictions are changing, they really do almost perfectly cancel out because the average accuracy only changes by about 0.2% across random seeds. So right, there's kind of 2 high-level takeaways here. One is the kind of disagreement rate across random seeds is larger than the accuracy gain from mini to large, which is changing the model size by a couple orders of magnitude. But the average accuracy is very stable, and so that's why we kind of never notice this normally, because we only look at the average accuracy. Okay, so are there any questions about kind of what's going on here?
So may I ask a quick question?
Mm-hmm.
So what is the intuition behind that when you change the random seed, I mean, the model or the model behave differently for the same data point?
So yeah, it's a good question. I think what this is sort of saying is that there's a lot of data points whose predictions aren't actually pinned down that well by the data. And so, maybe I would, so maybe like, if you bump the predictions around a little bit just from this training randomness, it's enough to kind of move it from one side of the decision boundary to the other. I kind of think of this as partly a consequence of kind of high dimensions, right? Like in low dimensions, if you kind of imagine this happening, it's kind of hard to imagine because like you kind of have the decision boundary and like it's probably pretty stable. There's like a lot of points on both sides. But in high dimensions, pretty much everything is empty space. Right, and so the decision boundary, moving around a bit can like totally flip a bunch of other points, just because there's lots of points in every direction, and so I guess I mostly think of this as kind of a consequence of high dimensions.
Yeah, so maybe because it's not convex, and we will, go to different local minima, and then we will get different.
I see. So, okay, I agree you could also be worried about non-convexity. My intuition is even for a convex problem, you would see this if your model was over-parameterized. Note that like you can actually get to 0 training loss on this particular task. So I guess you're always at a global minimum, but there's probably many different global minima because of the non-convexity. But I guess I don't have proof of this, but I would guess that even for convex problems, you would see this phenomenon.
Thank you.
Quick question. Is this somehow related to the complexity of the model? Because like here you show some more and more complex models, but maybe they're already very complex, as in, number of parameters. Did you observe something like that?
So, well, I think if you make the model simple enough, probably this phenomenon goes away. I guess whether that can happen in any regime where you get kind of any interesting test accuracy, I'm less sure about. I actually just don't. Right. I don't know. I don't think we've tried scaling this down further than the mini model, but I think that is an interesting question.
Thanks.
I have another question, very quick though. My intuition would be that the impact of the seeds would be somehow attenuated the longer. So if you train for longer, the influence is going to become less. I guess that's not true, but yeah, what your thoughts on that?
Yeah, so so I think that's a very natural question that we actually looked into. I didn't include those in these slides, but so one thing actually is that an additional source of variation you could consider is what iteration you stop the model on. And even if you wait like close to the end of training, the particular epoch you stop at also can lead to a fair amount of variation in the model prediction. So actually, even near the end of training, model predictions are changing a fair amount. I don't know. I don't remember if it was as large as this 10% number, but it's fairly non-trivial, I believe.
Thank you.
Just a quick question, sorry. So do you know this data is coming from which part of the distribution? Is it, for example, from the tail of the distribution or?
All of this data is just the regular development set. I think it's the development set probably is, I guess it's overall harder than the training set, mainly because it's probably filtered for kind of the more interesting examples. Although also it probably has less like label noise and things like that. But I don't think it's like the super extreme tail or anything like that.
Yeah.
Actually, if you go really into the tail, you can start to see differences even in the average accuracy. So there's this paper called "Birds of a Feather Do Not Flock Together," or do not generalize together, I think, which shows that if you kind of have hard enough OOD data sets, you get a lot of variation across random seeds as well.
Cool, yeah, really interesting.
There is one question at the chat.
I can't actually see the chat while I'm sharing screen.
Yeah, I can read it if it helps.
Sure, yeah.
It says, these phenomena somehow are connected to the sparsity of the input. Does the same hold true for vision tasks?
Yeah, that's a good question. I have not done that experiment. If I had to speculate, I would speculate that it does, but that's purely intuition. I haven't actually checked. Cool. Any other questions? Okay, cool. So let's figure out kind of what to do about this. So I guess in principle, if I'm worried about this source of noise, it's a random seed that I control. I could just average it out, right? I could train 50 different models with 50 different random seeds and just take their kind of average prediction. And that should kind of get rid of most of the noise. Also, I should say, the fact that there's these different predictions kind of indicates that ensembling should help, and I guess we see that ensembling does help. So we can effectively do that. We could just take this kind of average. So you can do that, but that's kind of expensive. We don't want to be training 50 models all the time. Actually, we did train 50 models. We trained 250 versions of BERT. We trained 50 versions of each of these 5 sizes, but I think we don't want to recommend that people be in the habit of doing that all the time. And it turns out even after you average out 50 models, there's going to be some noise remaining, and we'll see that on the next slide. So to kind of get a more concrete handle on these things, I'm going to look at this case study where we want to understand. I mentioned several axes of variation, but the one we're going to be particularly interested in is the effect of model size on individual data points. Where to get rid of this noise, I'm going to say on the kind of expected or average prediction across random seeds of these individual data points. So the kind of idea here is, okay, bigger models have higher average accuracy, but is that really uniform? Probably some data points get worse. So we want to understand, what are the data points that are getting worse and how often does this happen? And we want to not just kind of say that a data point's worse if it's worse just because of this random seed issue. So we want to know which data points have accuracy that decays on average across all of these random seeds. So that's what we want to do. And so to just kind of show some initial data, I guess first of all, so what could we do? We could take, n smaller models, n larger models. For each data point, look at the fraction of the larger models that get the answer correct, and subtract off the fraction of the smaller models that get the answer correct. And that's going to give us some estimate of whether things are getting worse or better for that data point. And so, we can look at a histogram. When n equals 1, we're just comparing one larger model and one smaller model. The histogram doesn't look that interesting. Most things don't change. A small number get better, and an even smaller number get worse. But probably some of the ones that are getting worse is just due to random noise and canceling out some of the ones getting better. So we want to kind of average over more models. So if we take n to be 50 instead, we get this histogram instead, where again there's a spike at 0. So this is sort of indicated that actually a lot of data points are fairly stable and don't vary across random seed. But then there are these data points that do kind of have variation. And for some of them, things are kind of getting better. And for a smaller number, things are getting worse. And maybe now that we have these 50 models, we might be willing to believe that the fact that this right tail is bigger than this left tail is kind of indicating something about these things in the left tail really are getting worse. Another kind of interesting thing here is there's not a spike at 0 or 1, which I would have actually expected, but it seems like it really kind of just decays. So that's what this histogram looks like. But then we could ask, okay, so how do we go from this to figuring out which data points are actually getting worse? Well, we could say, okay, everything to the left of 0 is getting worse. But if you do that, you realize there's kind of some subtleness here. Because the number of things that are strictly to the left of 0, it turns out are 21% of the instances. The number of instances that are at 0, like non-strictly to the left of 0 is, sorry, this is a typo. This should be, I think, 57%. I think I accidentally added 0.21 a second time. But I guess the point is 57% of instances are weakly to the left of 0, 21% are strictly to the left of 0. So there's kind of discontinuity at 0. And we should be kind of worried that like the things just to the left of 0 are maybe kind of leaking out from this 0 bin or stuff just to the right of it, just due to kind of statistical noise. And so we need to be a little bit careful. And I think one question you could think of is like, how far to the left of this 0 point do you need to be before you can be confident that things really are decaying? And there's pretty standard ways of handling this using like Fisher's exact tests and like Benjamini-Hofberg for controlling the false discovery rate. But it turns out those don't actually work very well in this case. They give very conservative estimates. And so I'm going to describe a kind of better approach, better in the sense that it is also rigorous, similar to kind of traditional statistical testing, but it's much better powered. You can kind of, it'll say that more things are actually getting worse and bounded away from 0 than if you use these kind of traditional techniques. So what's the kind of idea? So the idea is going to be a kind of computational simulation that kind of simulates a kind of control baseline. And it's going to turn out that if you kind of are doing better than or if you're above the baseline, then you can kind of use that to upper bound the false positive rate. And these kind of sort of simulation-based things have plenty of history in statistics. The bootstrap or permutation tests also are just kind of doing simulation rather than doing something analytical. And so this is kind of in that tradition. So the kind of intuition behind the baseline is, okay, we want to look at what happens when we move from mini to base, but some of that might just be random noise. So as a baseline, what happens when you just move from mini to mini with different random seeds? That's kind of, that should in some sense give us an idea of kind of what's happening just due to random noise. But so this is kind of the right idea, but there's two issues with it. So the first is that just as a sort of practical issue, we have 50 mini models and 50 base models. So for this mini to base, we can compare 50 models to 50 other models. But if we want to compare mini to mini, we have to split our models in half. So we could only compare 25 mini models to 25 mini models. And so then we either have to kind of decrease n for everything to have a kind of apples to apples comparison, or we have to double our computational cost. And both of those are pretty unattractive. So that's one issue. The other issue is like here, some of the models are small and some of the models are large, but here kind of all of the models are small. And so that's another, that doesn't actually matter so much, but it's another way in which things are not really apples to apples. And so we can fix both things at once by, instead of comparing mini to mini, we're going to compare a 50-50 mixture of mini and base to a 50-50 mixture of mini and base. So this is going to mean on average, the model size here is the same as the model size in our actual experiment. So that's more attractive. And then the other thing is that now we can use all of our data without kind of having to double our computational cost, because we can put 25 mini and 25 base on the left side and 25 mini and 25 base on the right side. And so now I still have 50 and 50, and I didn't have to do any additional computation. So this is kind of the better version of the idea, but it's pretty much the same basic idea. And it turns out that this idea can be used to upper bound the false positive rate. So I need a bit of notation to describe this. I apologize. So the notation is, I'm going to say accuracy sub I of a model is the fraction of models of that size that get data point I correct. Delta accuracy of I is the difference in this accuracy between base and mini. And then baseline sub I is the difference in accuracy just from this kind of control baseline from one of the splits to the other. So note that both the blue and the red can be either positive or negative. And so the theorem is that this baseline controls the false positive rate. So specifically, let's let decay be the true fraction of decaying instances. So the instances that really do get worse on average, if I had, say, infinitely many random seeds to average over. Then for any threshold T you pick, this decay fraction is bigger than the fraction of instances where this blue number is less than that threshold, minus the fraction of instances where the red number is less than the threshold. So this is kind of saying that this baseline controls the false positive rate. Okay, so are there any questions about this? Also, so Giovanni, should I be like leaving time for questions at the end? Like, kind of how much time do I have left?
Ideally, so you can, yeah. Let's say you can go on until 55, like 552. Yeah.
Okay, sounds good.
Yeah.
Sorry, there is a question on the chat. I don't know if it was answered earlier. It says, what does negative difference diff accuracy mean?
So negative would mean that more of the large model get it wrong than the small model. In particular, that's sort of what we care about, because we kind of expect it to be positive by default. But we're kind of looking for these instances where things are getting worse. Okay, cool. So I guess just to kind of show graphically what this method suggests doing, basically, we had these red and blue histograms from the estimate of the baseline. You want to turn those histograms into actually a cumulative distribution function, and then basically look for like the largest gap between the blue and the red cumulative distribution function. So this is kind of looking at different thresholds. Turns out that a threshold of around like 0.2 is the place where you would have the largest gap. And so that then allows you to lower bound the fraction of decaying instances. You have to be a bit, this is slightly non-rigorous because we're like picking the threshold adaptively, so that induces a little bit of overfitting. But you can also kind of control that. But I won't go into that. But basically, so if you do this, you can then ask the question, okay, what can I say about how many data points are actually getting worse on average? And so that's what this table is showing. So below the diagonal is how many things are getting worse. And above the diagonal is how many things are getting better. Note again, these are just lower bounds. But this at least gives you kind of a comparison between the lower bounds on the two different sides. So this is showing that kind of 2 to 6% of data points are getting worse. In contrast, 9 to 21% are getting better. And generally, there's about a 3-to-1 ratio between points that get worse and points that get better and points that get worse. Also, this 2 to 6% should be compared to like a 2 to 9% accuracy gain as we go across models. So the number of points getting worse is kind of comparable to the accuracy gain, which is kind of interesting. So it's saying like there really are a non-trivial fraction of points that are getting worse. But unfortunately, we actually haven't been able to find consistent patterns in what these points look like. So they are more likely to be mislabeled. We kind of like sampled 100 random points and relabeled them by hand, where we were blind to whether they were points that were getting worse or getting better. And the points that are getting worse do have higher label noise, but it's not enough to account for this overall drop. So most of the points are actually not mislabeled, and we didn't find other clear trends. So there's a kind of a mystery that we're still trying to investigate. So the kind of takeaway here is there's this data point level variation. It poses this statistical challenge. If you just kind of naively looked at what got better and worse, you would have been pretty misled. Like for instance, you would have said at least 10% probably for all of these, which is too high. But this challenge is surmountable because of this kind of false positive rate control result. Okay, so that's the first case study. I just only have about 8 minutes left, so I'll probably go through the second one a bit more quickly. But are there any questions on any of this so far? Okay. So let me kind of at least give you a flavor of the second part on measuring similarity. So I guess just to kind of say what this is about, we often want to measure the similarity or difference between different neural network representations. For instance, either different layers of the same network or layers of different networks. And the reason we care about this is it's kind of used as an interpretability tool to understand similarities and differences across architectures. So you can ask both like, how does the representation change as I kind of like go down the network and go through more processing steps? But you can also ask, do different architectures have kind of corresponding layers or not? And so there's this kind of whole subfield on defining different similarity measures using things like canonical correlation analysis. There's something called like orthogonal Mercutius transforms. There's this thing called centered kernel alignment. And so there's this kind of all these different methods, but we kind of wanted to understand them a bit better. And so to say why, I guess I need to define a bit more notation. So basically, given a data set of size n and a layer with p neurons, we can construct the n by p matrix A of activations. So this is sort of on each data point, like what value do all of these neurons have? And then when I talk about these similarity measures, they're actually distance metrics between different such representations. And when I said there's kind of all this work on defining good ones, this won't really be our focus, but there's this typical challenge, which is that you kind of need to be at least permutation invariant, because neural networks are kind of only unique up to permutation. And often you actually ask for some stronger invariance, like unitary invariance as well. So that's why it's kind of non-trivial to define these metrics. But the thing that I'm going to be worried about here is actually this kind of same noise sensitivity from the last part. Because notice that this is all defined on this matrix of activations. The activations are sensitive to random initialization noise, just like the predictions. And so we should be worried that this distance metric D is actually going to be quite sensitive to noise as well. And so to kind of get at this, we kind of defined a test that we think can give insight into this, where we say a good similarity metric should be robust to random initialization seed. So given two networks trained from different initializations, each layer in the first network should have a small distance to the corresponding layer in the second network. So the intuition here, right, is fluctuations for the random seed shouldn't dominate the metric. If looking at the same layer on different seeds gives like some huge distance, then that at least makes it harder to interpret what's going on. And I guess we need to say what a huge distance means. So we're going to compare to a baseline, which is the distance to far away layers within the same network. And so here's kind of what happens if you do this. It turns out that one of the common distance metrics, CCA, or this is a particular variant of CCA, really is very sensitive to the random seed. So I show here the distance from layer 7 of model 1 to other layers in the same model, and also to all the layers in model 2, which has exactly the same architecture, but just a different random seed. You can actually see that the distance from layer 7 to the other layer 7 is larger than the distance from layer 7 in model 1 to any other layer within model 1. So it thinks that like layer 12 and 7 in model 1 are more similar than layer 7 is to itself. Of course, you know, there could be plenty of differences between these two layers, because the random seed, you know, could affect what representations are learned. But I think it's still kind of troubling that, you know, presumably those distances should be smaller than the difference between like layer 7 and layer 12. So we found this quite troubling. There's this other metric CKA that you can kind of see is more noise robust. There are differences, but you know, layers 7 and 10 are more different than layer 7 versus 7 with a different random seed. So CKA is doing a bit better on this front. But there's kind of other tests you could run where you kind of want to be sensitive to the deletion of important directions. And actually, this test is a little bit weird because it's not like monotone invariant. So I guess I should say this is kind of, this second part is all kind of preliminary work, and a lot of this is hot off the presses. So take this result with a grain of salt, but it does seem like CKA can't really tell as easily when you're deleting important directions. The reason you shouldn't place too much stock in this graph is because I could define a like monotonically rescaled version of CKA, which would then still look good according to this metric. But I could, you know, I could make the orange line look like the green line. So this is something we're still trying to understand. But I guess the kind of general idea here is kind of interrogating these distance metrics by kind of trying to understand how things that we feel like we understand how it should affect the metrics actually affect them. And you often end up with surprises. So I think maybe I'll end by just kind of briefly reflecting on measurement overall. So I'd actually argue that a lot of what's left to do in machine learning is really about measurement. So in classical ML, we kind of focus on getting a low test loss. I'd say this is now kind of inevitable once you've defined the test loss, because we just have these huge models trained on lots of data. And so I think kind of the new thing we should be caring about in ML is actually specifying what test loss should be low, making sure it's something that's actually, you know, going to be what we want. Hopefully that's, you know, aligned with what humans want and good for society. And we need to just sort of understand that test loss and understand what it's implying. And I think the main tool for doing this is measurement. Okay, so I will stop there and take questions in the last bit.
That was absolutely amazing, Jacob. Thanks a lot for this talk. Well, I guess everyone will be clapping in their own way. I can see there were plenty of questions. So IS had 2 questions. I don't know if IS wants to ask them themselves or I can do it. I think the second question was about page 19, and it was, is this trained with SGD?
Yes, it is. Yeah, trained with SGD. Or well, I don't want to commit to SGD versus Atom, but it was trained with a stochastic gradient descent method.
Right. I guess this answers. And the other question. Okay. So yeah, IS doesn't have access to the microphone, so I'll try and relay questions. How much of the noise comes from the stochasticity?
So how much of it comes from stochasticity in the gradient method? So that's a good question, right? So I think there's like two main sources of noise. There's the random initialization, and there's the like stochasticity of the gradient steps. And I'm not. My intuition is that they both matter, but I'm not sure we've like very carefully teased those apart. So I don't actually know for sure which one would be the more dominant effect.
All right. And one final question by IS was, perhaps a similar experiment over a controlled data set would illuminate what fraction of data points gets mislabeled. So I think this refers to the previous part, kind of the final marking points. So they're suggesting a controlled data set. I'm not sure. Yeah.
So is the idea like a data set where you kind of know which data points are mislabeled, or what? I guess. Yeah, I guess I'm trying to understand exactly what the suggestion is.
Yeah, I didn't get the question either.
So IS basically, I don't know if he means that, but his latest question is about the data order being fixed, and then he's mentioning essentially adversarial spheres. I think there is a recent paper where even the order of the data.
Okay.
Where the order of the data
Actually,
can matter a lot.
Sorry, there was a fire alarm here. I think he even linked on a paper where the order of the data was shown to be able to poison the model somehow. This is why I think he asked if the order of the data is fixed.
I see. That's quite interesting. Yeah. So this is the original adversarial spheres paper, or there's some follow-up that's about data ordering?
No, I think there's a recent paper. I don't know if it's the one. Well, they linked it in the chat if you want to have a look.
So I'll have to take a look at that. I actually hadn't seen that paper.
I did have a question on similarities between models. Something quite interesting, particularly in privacy, is of course to understand models that were trained on some data and the same data with some elements removed. Do you think a similarity or distance notion could work in that case too?
Right. So I guess this is sort of one of the reasons why I care about this kind of specificity test, because if you remove the one data point and then retrain, you're going to, I guess a lot of stuff is going to change, right? Because you're also changing the random seed almost necessarily, or at least the meaning of the random seed is sort of going to be different now. And so I guess, okay, if we're hoping for privacy, then of course, maybe that's a good news if retraining just changes everything and creates a large distance. But I think what I'm worried about is that the metrics we've picked so far, since they weren't kind of caring so much about this noise sensitivity, there could be better metrics that actually are able to reject that noise and would kind of be able to tell if you'd like, probably, I imagine removing a single data point is not going to lead to a large distance, but maybe like a group of related data points, like you could actually notice, even though you can't notice that before you've gotten rid of the noise. So I think that is kind of one of the reasons why I care about this noise sensitivity.
Cool. Thank you. Yeah. So are there any more questions? Well, if not, I'm going to thank again Jacob for his talk, and thank you all for bearing with our difficulties, organizational difficulties today. And we'll meet you in 2 weeks with a talk by Nicola Carlini. So yeah, stay tuned. Thanks a lot again, and yeah, speak soon.
Cool. Thanks everyone for your great questions, and you should all go to Nicola's talk because he is great.
Cool, and you can come too, of course.
We'd
We'd love to see you too. Then. Okay.
Thanks very much.
All right.